This is the Chapter 8 Practice Test Walkthrough. Question 1. Which combination of bonds is present in this molecule? Well, we have a triple bond, 3 bonds, and the first bond is always going to be a sigma bond. So you always have one sigma bond. And then anything else, if you have a double or a triple bond, the first one is still a sigma, but the additional bonds, the second and third bonds, are always pi bonds. So in this case, we have 3 total bonds, which means you've got 1 sigma, and you're going to have the other 2 that make up the second and third bonds are going to be pi bonds. So that is choice B. Okay, which of the is true of the strength of the bonds shown above? So we've got a single, a double, and a triple bond here, and we want to remember that the more bonds there are, the stronger and the shorter they are. Okay, so more bonds, the more bonds there are, the shorter they get. And the shorter the bonds, the stronger the bonds, because the atoms get closer together, the protons in the nucleus get closer to the electrons on the outside. So the shorter they are, the stronger they are, which means the most bonds you have is going to be the shortest and the strongest. So you can eliminate the choices that compare the triple and single. So the bonds in C are stronger than the bonds in A because there's a double bond there compared to a single bond. And then the second question, which has the weakest bond? Well, if shorter and more bonds mean stronger, then that means that fewer bonds are going to be the weakest. Right? So remember, fewer bonds are weaker. The more bonds there are, the shorter they get, and the shorter they are, the stronger they are. What type of molecular shape is shown here? So you need to look at the center atom, which is the darker one in the middle. There's 1, 2, 3, 4 bonds around that central atom. And if you look at the chart that shows you the shapes, you'll find that 4 bonds, and there's no lone pairs, these are all bonds, 4 bond pairs equals the tetrahedral shape, which is what this picture is showing you. So tetrahedral is answer choice B. Which of the following has polar covalent bonds? Well, process of elimination, that's a polar bond in A, NH3. KBr is a metal nonmetal. That's not a covalent bond. O2 has 2 identical things, so the only choice here is A, because B and D are both ionic. How many valence electrons are in PO4, 3, the phosphate ion? Well, the phosphorus has 5 valence electrons. Each of the oxygens has 6, and there are 4 of them, so that means 24. And then you have to add 3 extra electrons for that -3 charge, which means there's 3 more electrons than usual. So you've got 29 from the atoms plus 3 for the charge, which is 32. Answer choice B. Which is the correct name for the compound NF3? Well, there's 1 nitrogen, and when there's only 1 of the first element, you don't need a prefix on that. And then there are 3 fluorines, and the prefix for 3 is tri, T-R-I. So it's going to be trifluorine, and nitrogen doesn't need a prefix. So nitrogen trifluoride, you have to remember to change the ending to fluoride, is the correct answer. The other 3 have either the wrong prefixes or prefixes where you don't need them. So A is the choice. What is the correct answer for P2O5? All right, 2 phosphorus, 5 oxygens. The prefix for 2 is di, so you need a prefix for this one because there's more than 1. So it's going to be called diphosphorus. And then 5 oxygens, the prefix for 5 is penta, and it's pentoxide. Because oxygen starts with the O, we can drop the A from penta, and it's just called pentoxide. So diphosphorus pentoxide, choice D. Which of the following is an exception to the octet rule? Well, you could figure this out by drawing out the Lewis structures even without all the extra electrons. Beryllium, BH2, only has 2 bonds on it. And if you did the math out, you'd find there's no lone pairs. CH4, 4 bond pairs, that's a complete octet. pH3 has 3 bond pairs and a lone pair, that's 8 electrons. And then water has 2 bonds and 2 lone pairs, that's 8. So the only one that's not an octet is BH2 here. Why is it not necessary to use Roman numerals in the naming of covalent compounds when you use them in ionic compounds? Well, ionic compounds, the reason we need the Roman numerals is because in an ionic compound you have to make sure the charges match. And sometimes you can just figure that out by knowing what the charges are. But iron sometimes is an element that can have more than one oxidation state. Sometimes it's a +2, sometimes it's a +3. So you need to indicate in the name which one we're talking about. That's what the Roman numerals are for. In a covalent compound, you don't need to do that because there are no charges involved. You use the prefixes to tell me how much of each element there are, and there's no need for the Roman numerals because we're not really working on making it neutral from the charges. And so again, it's the oxidation number that can be different in an ionic compound that requires the use of a Roman numeral, and we don't have that in covalent compounds. Which of the following is capable of forming an incomplete octet in its molecule? Well, if you look at just the elements by themselves, okay, boron has 3 valence electrons. Carbon has 4. Phosphorus has 5 valence electrons. Oxygen has 6, and selenium has also 6. So if you think about the number of bonds you can have here, we're talking about an incomplete octet, which means less than 8 electrons. Boron, if it only formed 3 bonds, would have 6 valence electrons. Phosphorus, even if it formed 3 bonds, it would then end up with 7. It would actually end up with 8. Carbon's going to end up with 8. Selenium's going to end up with 8. So boron's the only one that could be incomplete. The formula for copper 2 chloride, remember Roman numerals we just talked about, tell you the charge of that atom. So copper 2 means 2 positive, and chlorine is a 1 minus. So it takes 1 copper and 2 chlorine for the charges of positive 2 and negative 1 to cancel out. How many protons, neutrons, and electrons does carbon-14 have? Well, carbon has 6 protons. That's its atomic number. So that tells you that there are 6 protons, and it's a neutral atom here, so there have to be 6 electrons as well. So we're talking about 6 protons, 6 electrons, and what we need to figure out is how many neutrons there are. The way to figure out the number of neutrons is by subtracting the protons. So we get 6 protons, 6 electrons, and then to find out the neutrons, you take the mass, which is 14, subtract the protons, and that gives you the neutrons. So 6 protons, 6 electrons, 8 neutrons. Last of the oldies but goodies here, conversion. All right, 3.945 liters to milliliters. So we put 3.945 over 1, and then on the other side we know that 1 liter is equal to 1,000 milliliters. So we end up multiplying 3.945 times 1,000, which is 3,945 milliliters. Alright, so we're doing some naming. This is carbon with 2 sulfurs, so it's carbon, and then the prefix for 2 is di, so disulfide. That's the name. And then we have to do our Lewis structure, so we need NaSl. Oh, we're going to do carbon monoxide. Okay, that's CO. Carbon monoxide means 1 oxygen. That's all the ones we had to fill in there. So NaSl for carbon disulfide. We've got a carbon and 2 sulfur, so if we line them up, you put the sulfur on either side, put the carbon in the middle. 3 atoms, none of them is hydrogen, so you multiply 3 times 8, you get 24. For A, you look at the valence electrons. Carbon has 6, each of the sulfurs has, carbon has 4, each of the sulfurs has 6, so that's 16. And so 24 minus 16 is 8 shared, so we need to make 4 bonds, 2 on either side. And then 16 minus 8 is 8 leftover electrons. If you put 4 on each of the sulfurs, that gives you your 8 and gives all the atoms 8. Is there resonance here? No, there's no other way to draw this and still be correct. The shape is 2 bond pairs. Remember that the double bonds only count once. 2 bond pairs, no lone pairs on that central carbon, which makes it linear. And the hybridization of linear is sp. Is it polar? No, because there's sulfur on both ends. It's the same thing. So carbon monoxide, you've got 2 atoms, neither is hydrogen, so the N is 16. The available is 4 plus 6, which is 10. Subtract that, you need to share 6 electrons. That's a triple bond with 4 left over, so put 2 on either side. There's no other way to do it for resonance. You've got 1 bond pair and 1 lone pair on the carbon, but you've only got 2 atoms, so it has to be linear, which again makes the hybridization sp. And it's polar. If you do the subtraction on the polarity, you'd find that carbon becomes slightly positive and oxygen becomes slightly negative in this molecule. So moving on to nitrogen trihydride, you've got a nitrogen with 3 hydrogens around it. And so we're going to assume that you've got a bond to each of those, but we'll do the NaSl too. So the N is 2 times 3, because each hydrogen needs 3, plus 8 for nitrogen is 14. Available, 1, 2, 3, each hydrogen has 1, nitrogen has 5, that's 8. So you need to share 6, there's your 3 bonds. You have 2 left over, they can only go on the nitrogen, never put them on the hydrogen. There's only one way to draw it, so no resonance. There are 3 bonds and 1 lone pair, which is trigonal. I'm not going to be able to fit all in here. Trigonal pyramidal. So trigonal pyramidal is the shape there. The hybridization is sp3, and it is polar. The bonds between nitrogen and hydrogen are polar, and you've got lone pair at the top. It's a different shape, so you've got a plus and a minus. Silicon tetrafluoride. Silicon in the middle, 4 fluorines. The N, you've got 5 atoms with no hydrogens, so 5 times 8 is 40. Available, each fluorine has 7, that's 28. Silicon has 4, that's 32. 40 minus 32 is 8, so you can make 4 bonds, and then you've got 24 left over. Put 6 dots around each fluorine, that is 24 lone pair electrons. There's no 2 ways to draw this, so there's no resonance. You've got 4 bond pairs and no lone pairs on the silicon, which makes it tetrahedral. That has a hybridization of sp3, and it is nonpolar because it's the same all the way around. All those bonds are polar, but the molecule is nonpolar because it's even. Okay, going again to draw Lewis structures and define the shapes. So CO2 is 3 atoms, no hydrogens. 3 times 8 is 24. 2 oxygens are 6 each. Carbon has 4. That adds up to 16. So you got 24 minus 16 is 8 to share. There's your 4 bonds. And 8 left over. Put 4 on each oxygen. And you've got 2 bond pairs around the carbon, no lone pairs. That makes it linear. For pH3, you've got 4 atoms, but 3 of them are hydrogens. So you need 2 for each hydrogen. That's 2, 4, 6, plus 8 for phosphorus. So your need is going to be 14. Your available is 5 for phosphorus, plus 3 for the hydrogens, 1 each. That's 8, leaving you 6 shared pairs, or 6 shared electrons, which makes the 3 bonds, and then the 2 lone pairs. 2 lone pair electrons make 1 pair on the phosphorus. So we've got 3 bonds, 1 lone pair. That makes this trigonal pyramidal. All right, water, H2O. We got our NaSl. We can put it out here. We know we're going to have an oxygen with a hydrogen on either side. And the need here, 2 hydrogens times 2 is 4, plus 8 gives you 12, the 8 for the oxygen. There's 8 available, 6 from oxygen, 1 each from the hydrogen. You need to share 4 and have 4 left over. 2 bonds, 2 lone pairs, and then 2 bonds and 2 lone pairs makes the shape what we call bent. Last one, silicon tetrachloride. You've got silicon in the middle, 4 chlorines around it. Our need, we've got 5 atoms with no lone pairs, that's 40. Available, 7 from each chlorine is 28, plus 4 from silicon is 32. The difference there is 8 shared. There's your 4 bonds, 1, 2, 3, 4. you've got 24 left over. So put 6 on each chlorine. That makes 24 lone pair electrons, and everybody's filled up. And with 4 bond pairs, you've got a tetrahedral shape.